This is the next keynote, and the next keynote speaker is Pierre Bégout, and he's from IMT Atlantique, and he will be talking about digital twin and mixed reality for the industry of the future. Pierre is a final year PhD student at the campus Brest of IMT Atlantique, and he's working on digital twin in industry for the training of operators. And also, like with all the other keynote speakers, we have a trailer for the keynote, and Pierre, you can already come over, and we'll show the trailer, and then I will hand over to you.
In the context of industrial evolution and the transition to Industry 4.0, the digitalization of industry is necessary. The digital twin is the keystone to this transition by providing a complete digital factory, which enables new ways of simulate and predict behaviors and new ways of training new operators. During my keynote, I will talk about the digital twin, its usage in industry, and its usage in combination with mixed reality. And I will finish by presenting a use case in a French factory.
Perfect. So yeah, I'm already looking forward to it, and as you know, we have the Slido, and I highly encourage you once again to put your questions to the Slido. Even if you're in the audience, then you don't forget them, and you can just put that you're in the audience. And besides that, as I said for the previous talks, for the keynote speaker, it's always good to have some questions, because then you see that the people were attentive and are interested in your topic, and therefore if you could think about one question each, that would be fantastic. So yeah, just be encouraged to also ask questions after the presentation. And that said, Pierre, I hand over to you, and looking forward to your talk.
Okay. So hello everybody, I'm Pierre Bégout, and I'm happy to present this keynote about digital twin and mixed reality for the industry of the future, or Industry 4.0. So first, a little presentation about me. So I have an engineering degree in informatics and cognitive science, so it was in Bordeaux. In my last year of PhD, so at IMT Atlantique, and it's a PhD with a company. So I'm working with ELM Leblanc, a boiler manufacturer located in Drancy, so in the north of Paris. And my supervisors are Thierry Duval and Sébastien Kubicki at IMT Atlantique. So we'll start by a little context about how the manufacture works, how the industry is currently operating. So first, we have the raw materials and parts which are produced. Then they are shipped to the manufacturers. So in our case, ELM Leblanc, which manufactures the boilers, in my case. Then these products are shipped to wholesalers who will sell the product. So right now, everything in the industry works in tense flow, so they tend to not have stock because it's expensive to maintain. The production orders are planned in advance, so usually we have a big order of products planned months in advance, and there's a high inertia to change, so it's very hard to induce change in the factory. And so what happens when we have a raw material shortage or a problem with the shipment? The problem is everything stops and we cannot manufacture anything. Like we can see right now, we have a semiconductor shortage. We have raw material shortage. Right now, it's hard to find wood, to find metal. In case you didn't know, we have a problem with a pandemic. So it's hard to keep manufacturing. And we have new laws that will induce change in industry. For example, in our case, we were manufacturing new boilers working with fuel, and the government passed a new law which forbid these new boilers. So right now we have a whole new assembly line that doesn't work because of this law. So in this complex and volatile world, we need to evolve to make industry evolve. We have to make the industry needs to be more flexible and adaptive, and more reactive to change. We need to build smaller quantities but more customized to demand, because now we can't manufacture very big orders. We have to change this kind of things, and we have to modernize the factories by using IoT, big data, mixed reality, and a digital twin. So we'll first explain what is a digital twin. So the first definition was in 2003 by Michael Greaves. So it's a virtual representation of a physical product which contains all the information about the said product. More precisely, because this definition was changed in 2014. So we defined 3 parts for the digital twin. So we have the physical product, which can be a machine, a whole system, or just a screw, for example. We have the virtual product, which is a copy of this product but virtual. And we have a bidirectional flow of data between these two twins. So to be more precise, we have the physical twin, so single part or complex system. And we have data, and this physical twin will provide data, which can come from internal and external sensor. And this sensor will be part of the physical twin. We have the historical data of the product, like every maintenance which has done on this product, and we can have human input that will send data, for example. And the digital twin, so the virtual product, it's the virtual representation of the physical twin, and it can contain several modules. So, for example, a 3D model, a behavioral model, a module to make simulation, and a monitoring module. So the data coming from this digital twin are the simulation and monitoring results, and again can be human input made on the digital twin to be sent on the physical twin. The main application of the digital twin in the industry are product health management or predictive management. It will be used in production to design new products and to train and help maintenance. So the simulation, to make simulation, we'll use behavioral models. For example, what will be the reaction of the product if we exert pressure? We will use data coming from the physical twin and user input, and with these informations, we can have a total simulation of, for example, an assembly line. And we'll use the result of this simulation to predict and adjust the production, or to design new product or process. For example, in these pictures, you can see on the left we have a simulation of this part, and we exert pressure on this part, and we will simulate the displacement on the x-axis to see how the parts will react with the movement of the system. Or we can simulate the machining of a part. So we can use the digital twin to monitor a total assembly line, for example, and then again we will use the behavioral models, and the data coming from the physical twin. So it will be used to detect problems, to adjust production, or just to know where we are in the production. For example, usually we have production orders for one day. For example, we have to produce 60 boilers. With the digital twin and the data coming from the physical twin, we know every time how many boilers we produce. So digital twin can be used to design new products or new systems. So this time we will not make a copy of of an existing physical twin. We will start with the digital twin to create a new product. So again, we will use behavioral models. So we will enter the behavior of the future system. We will simulate, and we will use 3D modeling to know what our physical product will be. So we can design new station, new machines. So in production, we will mainly use the digital twin to monitor the production, but we can use it to update the layout of our production lines virtually to avoid moving every part by hand, etc. And to make optimization of production orders. For example, when we have different products to produce, using the digital twin, we can simulate and test to see which product we will produce first to optimize the product change. So because sometimes we will modify the workstation according to the product to be produced. So digital twin has many use and many good use in the industry, but it has its flaws. So several issues remain. For example, the digital twin generates a lot of data, and this data is difficult to sort and to store, but also to secure. It's hard to visualize and interact with the digital twin naturally. So usually you will have a lot of data, and it's hard to detect to know which data will be useful to you at the moment. And right now it's hard to create a digital twin of an old factory, because it's easier if you have a lot of IoT and big data in your factory. And right now most of factories in France and I guess the world are not very up to date on these new technologies. So to answer some of these issues, like visualization and interaction, the use of VR or AR, so virtual reality and augmented reality, enables a simpler way to visualize and interact with the digital twin. So to use the example earlier, we can use AR to do the direct monitoring of a machine. With the display of information directly on the physical twin, information that we cannot see and cannot know when we are in the production line. We can use the AR to help the training and maintenance of machines. For example, here it's an assembly assistance, so it will display information about the assembly process directly on the workstation. And we can use VR to design and simulate new workstations. For example, in this work, we have the ergonomic assessment of new workstation and the simulation of new workstation. So these use are very interesting, and I will now present a use case we are working on with on the digital twin and the mixed reality. So the Iron Man project, it's a project I'm working on. And so for more context on this project, ELM Leblanc has a seasonal problem. So we on the high season, so it's during winter, we have a workload increase because there's a lot of boilers who are broken, and so we have a lot of order of new boilers. So we have to hire a lot of temporary operators to work on the assembly line. And so we need to train these operators. And right now, the training process lasts between 3 days and 2 weeks, and require the help of an experimented operator to train new operators. So the production line is not working efficiently. And during low season, so we have to, we don't know, the client requests are unpredictable. So we need to be flexible. So we need to be able to the workers need to be able to work on different workstations, because right now they are specialized in one workstation or two, and we need to put them on different workstations. So to answer these problems, we started the Ironman project. Oh, sorry, we have some French. So it's a project in 3 years with 5 PhD students. So one working on AR acceptance for the workers, so to see if there is problem with wearing an AR headset for a long time. One PhD on workstation modeling, so my part. One PhD on AR training, one in environment and gesture recognition, and one PhD working on 3D simplification. And the goal is to train new operators in real time on the assembly line, to develop the operator's versatility, to increase the flexibility of the production, and finally to prevent work-related disease during training, because sometimes during training the operators are trained with wrong positions, and it develops work-related disease like tendinite. I don't know in English, but some workers develop problems. And so I will speak more about my parts because I work on the digital twin. So the question is, how do we allow operators to be actors in the creation and maintenance of the digital twin of their workstation? So how do we create a digital twin which is loyal to the factory? So how do we create an exact representation of the workstation? Which element do we need to display in 3D to be used as spatial anchors? So the goal is to have 3D elements representing the workstation, which will be used to lock informations about these elements in case of modification. I will explain more later. And how do we allow operators to upkeep the digital twin to match the physical twin? Because if we want to train operators using AR, we need to have an exact. We need the instructions to be precise, and so usually operators they like to move the component boxes to simplify their work, and so we need to allow the operators to modify the digital twin to match the physical twin after modifications. So in order to do that, we went on the workstation to to study them and to know which elements are important during work. So this is a workstation from LM Leblanc. So it's composed like this. So we call that the supermarket. So it's a big shelf containing the component boxes and which contain the components. We have the tools. So I don't know if it's visible here, but they are screwdrivers, electrical screwdrivers. And we have the assembly zone. So here we have an assembly bench, but on some workstation you can have test bench, for example, electrical tests or hydraulic test. And so the parts that are important to copy, so the important parts in the digital twin are these parts, so the component boxes, the tools, and the assembly bench and test bench, because these are the parts which the operator we will interact with. So we call them the interaction zone. So these are the parts that are important, and these are the parts that will receive AR informations, AR training informations. So these are the parts that we need to copy and to have 3D model of. Then we created the digital twin models based on the observation on the workstation and the BOM file, so bill of material file. So it's like this. We have the digital twin, so we have all the factory data, so all the information about the components present on the workstation, all the parts, so it's a big database containing everything. And we have the 3D models of the interaction zones. So this is our digital twin. So it's a digital twin, but it's just a part of a digital twin because we could have simulation models and behavioral models, but we didn't add these parts yet. And it's linked to the real factory by an AR tracker. So right now we use QR codes, but we could use any AR tracker. It's not the most important part. And we added the augmented operator in this model. So an augmented operator is an operator wearing AR headset, and the operator will make the connection and the upkeep and the updates of the digital twin. And so then to allow the augmented operator to interact with the digital twin and to superimpose the digital twin with the physical twin, we developed WARD, so Workstation AR, Augmented Reality Digital Twin. It's an AR authoring tool. It's connected to the digital twin, and it will allow the operator to superimpose every part with its physical twin. So it will present to him one by one. He will place them. And if the workstation is modified, he can then just displace the digital twin to match the physical twin. Right now it works like that. Our goal is to be able to make the update our goal is that the update will be automatic. So right now we don't track every part, and the goal is to track every part. In the model, every part is tracked, but in real life, it's hard to put AR tracker on every interaction zone because some boxes come from retailers, so we can't put QR codes on everything, and when the box is empty, it's replaced. So we cannot put trackers on everything. And so this digital twin will be used as spatial anchors for AR assembly instructions. So when we update the workstation and the digital twin, the instructions are also updated. So to be more clear, I have a video. We don't need the sound. So right, this is presented like that. So the operator will match the QR code. So you will see a little the holograms will not perfectly match everything like that. The QR code is supposed to be superimposed, but we have it's not perfectly matched because when we record with the headset, we have it's not perfectly matched with the recording, but in real life it is. Okay. So then the application will get every information about the workstation. And then every part, every digital twin will be presented one by one, and we will place it in the physical twin to match everything. I don't know if okay. And then to test our product, we made an experiment in which we had the operators had 36 digital twin to place, and we compared our tool with the one from Microsoft, so Dynamics guides, and it appeared that our tool is easier and faster to use, and furthermore, our tool is connected to the digital twin, and guides is not. So we had to put every twin. We had to log everything one by one in guides. So we are quite happy with the result. You can see that it's much faster because we want to we tried to make it as simple as possible. So as few information as possible, and we wanted the interactions to be the more natural as possible. Okay, so to conclude, the industry needs to evolve because we need more agility and flexibility and modernization. So the digital twin enables new ways of production and flexibility. So we can simulate and monitor to avoid problems. We can design new products and new assembly lines to adapt faster and easier. And we can, by having production monitoring and simulations, we can make a more personalized production because we can adapt easier. And with the combination with AR or VR, we can train and assist workers more easily, so the training will be faster and in autonomy and directly on the assembly lines. But it's hard to have a consensus on the generic digital twin framework, because right now you can make a generic digital twin, but every operation has its specialties, so it's hard to make something that will adapt to every factory. And it's hard to deploy and maintain a digital twin in all factories, so sometimes you don't have every information necessary. So that's it. Thank you for your attention, and if you have any questions.
Okay, thank you for the talk. Actually, there are quite some questions.
Okay.
But I would like to start with my question.
Okay.
I was wondering, how about in the practical side? What kind of software are available? Open source or commercial? If we want to play with digital twin, what are the main players there? Are there some GitHub projects that we can create our digital twins and model and such?
Yeah, right now there's no generic framework, no. So every article I saw, every example I saw, there was the digital twin was made from scratch with a homemade framework. So right now it's hard to find something that I have a new company, I have a new product, I want a digital twin of this product, but I have to make it. I cannot use the modules. I cannot grab the module and put it in my digital twin. So right now, yeah, it's hard to find.
Would you say that like there is a gap then? Like that would be nice if there's a framework that we can use some sort of tool set.
It would be nice if we had a simple digital twin base that you could evolve for your needs. And right now we have nothing. So yeah, we created the whole database. We grabbed the whole all the information from the factory. There are bills of materials that are very hard to read when you're not in the field. So we had to adapt and to ask them. And so we deployed in our factory, but we deployed in another one. And right there was some. It wasn't even the same bill of materials, so it wasn't even a standard. So we had to. It was our model was usable, but it was hard to adapt to every factory. So right now, yeah, that's a problem.
we have a lot of questions. This never happened before. Maybe I may need to select, but okay, let's start. Maybe we can even finish in short all of them. First, how do you make the digital twin? Is it like training, like a machine learning model, or is it fitting parameters like more normal simulation?
For the behavioral models, or
It says how can you create a digital twin?
okay. So it depends what you want to have in your which module do you want, because if you want just like us a representation of the workstation and the assembly lines, you can just have the information stored in a database with like for example we have assembly line number 1, and in this assembly line we have 12 workstations which contains 31 component box with these components. And so you can just have this information, and if you have the 3D models, you can use the 3D models to match the physical twin. So in our case, it's very simple, but if you want to make simulations, then you will need all the information how the workstation works. If you have machines, you will need the information about the machines, how many orders you can produce in like 1 hour, how it operates. So you will need. It depends on what you want to do and what you need, and so it can be very simple and it can be very complicated. So it depends on the scope of the digital twin that you want.
How many
maybe let me continue with a follow-up question. So how long did it take to create the digital twins for this setting? So is it hours, is it days, is it weeks?
In our case, it's a simple one because we don't have a lot of information. And in our case, the creation of the database took like 1 month because we also needed a communication between the database and the AR headset. And so because usually in industry it's on the assembly line, usually internet is not very good because it's protected. So we need to go around this. So in our case, 1 month to have the database, so the digital twin data. The 3D models, it depends because we have some, and when we don't, we use just a box to represent a model. But it depends also if you have all the data available of your workstations, because we have this data, but for example, the tools, they are not in the bills of materials. So when you have a screwdriver, it's not in the bills of materials, so you have to check and you have to go on site to see. So this information, it's hard to have. But I'd say 1 month for the database and 3 or 4 months for the AR app to have a stable version that works well.
And who was doing the job? Was it you doing the job, external people coming into the company and then creating it, or did you have the experts from the company doing it?
For the database, it was me and the other PhD student working on AR instructions, because we store the instructions. We consider the instructions that the instructions are in the digital twin, because it's technical instruction of the workstation, so we consider that they are part of the digital twin. And so we were 2 working on that. So yeah, it was just the 2 of us, and we made 3 apps, because we have 1 app to match the digital twin, 1 app to create the instructions, and 1 app to visualize the instructions. So
Okay,
and I'd say everything took us 1 year to make.
Okay, very, very interesting. And could you give some more details about what this digital twin is? So is it a MATLAB model that is running, or is it a Java code, or is it a Python script, and which aspects are modeled within this digital twin?
Yeah, but we have a simple database which contains everything. We are not finished, but we wanted to develop a web interface to send that data in this database. And then we have a web service made in C# communicating between the database and the AR apps. And the apps are made with Unity and MRTK, so the mixed reality toolkit from Microsoft. And we are using HoloLens too.
Okay, nice. do we have? I can also still has a lot of questions. Do we have some questions from the audience in this in the room? Yes, there's one question. Christian, could you bring the microphone upstairs?
You have water there as well.
Ah, okay. Thank you.
In case you need more, I can provide you.
Okay, thank you for your presentation. I have a small question. The virtual machine that I don't know if this virtual machine depend the data collected by this virtual machine depend on the sensor that contain the physical machine. I don't know if you construct the virtual machine depending on the physical functionality of the physical machine. And after collecting all the data, how do you? What is the decision that is taken with the AI model to? I don't know to continue the work, your workflow. Okay.
So you wonder how do we make the digital machine with using the data from the
Yes.
because okay, so maybe I wasn't clear. So the definition of the digital twin, you have the physical and the digital, and there are data coming from both of them. Which will so the data will come from both of the twins, and so the data coming from the physical twin will be used in the simulation models, or we will use them to, for example, if you have to know what is the pressure in an oil tank, for example, and so you will use the data coming from the sensor. You will get it in your virtual, your digital twin. And if you need to, maybe you need to know if you can add some oil or you can remove. And so you will simulate in the digital twin what happens if you put some more oil, okay. And you will know the level, your internal pressure. You will use the data from this one. And with the behavioral model you have, you know that if you have the pressure, this oil level and pressure, if you add oil, you know it will explode, for example. So you use the information that you have and the information that you know from the specificities of your physical twin, and you will use them to simulate and to try and to try again to see what you can do.
Okay. It's right. It's right. Okay. Thank you.
Any other questions from the audience? Mike is coming. Thank you.
Hello.
Hello.
Thanks for the presentation. I didn't see when you show the video of the IR example. Did you track the hand movement by a controller, or did you use something basic?
No, yeah, it's in the HoloLens 2 you have a hand tracking module, and so it will track your hand and your fingers, and you can interact with the 3D elements naturally. So you can push buttons, and you can grab 3D models and move them. And you can resize them with using two hands. So we use this technique because it's easier to apprehend this manipulation for operators that never used AR headsets. And that's why it's in our experimentation, we saw that it's easier. Our tool is easier to use than Microsoft's because they use the distant interaction. So they use a raycast from your palm to the 3D models, and then you have to pinch and you grab it from a distance. And so using it, just grabbing directly, it's easier for operators.
Okay.
And so that's what we used. It's from the HoloLens 2. But if we had to use a controller, we couldn't use it in a factory environment because when you give them sensitive elements, usually they are broken in like very fast. They tried to give them tablets, but at first they use it with their finger, then it's with the screwdriver. So you have to be careful. That's why just having your two hands, it's easier.
And could you track the data of the on move for the future? Maybe train robotic arms to do some of the easiest tasks.
You could track and to train an AI to reproduce the arms. It could be a possibilities, and we have a PhD student working on gesture recognition. So they will use to. For now, it's to validate, for example, if the operators did the task correctly, to switch to the next task. But in the future, you can have a lot of use of this tracking and this learning from your movement.
Okay, thanks again.
Any other questions? While we are thinking, let's pick up from the Slido. How many digital twins have you implemented or are you using in factories?
What?
How many digital twins have you implemented or are you using in the digital factories?
I'm not sure.
Maybe an estimation. I just clicked it, answered, it's vanished.
Okay, I'm not sure I understood the question. How many digital twins do we use?
Or are you using in the factory or have you implemented for the factory?
Yeah, okay. So but it depends on the workstations, because when you say digital twin, you can consider if you have the whole factory in your database and you have the whole model of the factory, you can consider it like one digital twin. But I like to consider each interaction zone as its own digital twin, because each one is represented and we have the position. So it depends on the workstation. For example, the workstation I made the tests on is composed of like 36 component box, and I represent also the workbench. So we have 37 digital twin on this workstation. So if we implemented the whole factory, we would have a lot. Yes. I cannot say. Yes. But it depends on what you consider your digital twin. If you consider each part individually, you have a lot. If you consider the factory as one digital twin composed of a sub-digital twin, you have one big digital twin. It's as you see it.
Let's pick this one. How expensive is a digital twin and what is the benefit for the customers? Amount of cost savings, for example, maintenance cost.
Expensive, it depends. But it's you have the human cost, like yes. For example, the paying the engineers and the PhD student. I don't know how you want to implement it. Yeah. The benefits for the customer depends on what you want to do. If you want to be able to simulate the production line to make sure everything works, or to monitor, it depends on what's the use you have for a digital twin. So the benefits, there are lots. You have, for example, if you have to design new production lines, you can do it virtually, and it will take a lot less time. So you would have your new production line way faster, and it will be less human cost, because you won't have to move every part. Because in our factory, that's what they did, because we didn't have the digital twin ready, but they made a whole new production line by hand. So they had like big carton box, and they were like, okay, so this would be workstation number 1. Okay, this is the dimension. Oh, okay. Oh no, because we have to put the test bench here. So yeah. And doing it virtually with everyone who is connected, like, okay, no, we can move it here. That would be way faster. So you could save like 1 month of work. So the benefits, there are lots. It's just hard to imagine when you'd never tried and never tested one.
How are the physical and digital twins connected? How is the change in the digital twin replicated on the physical one?
Okay. So right now they are connected with an AR tracker, but Usually we, in our case, we connected them with AR, so the AR tracker was the connection. The change on the digital twin are not replicated automatically because we don't have a connected production line.
Yes.
But if you have a production line full of IoT and, for example, automatic with automats, etc., you could make change on your digital twin that would be replicated directly on the physical twin if you use IoT. In our case, we have like 0 IoT in our factory, so we cannot replicate directly a change from the digital twin to the physical twin. But if you have like a machine that's connected by IoT or, I don't know, internet, anything connecting the two, you could like say, or you would change the pressure on this bolt, etc., to make these new things, and the change would be like almost instant. It depends on what you have at your disposal in terms of connectivity between your physical twin and your digital twin.
Are there digital twins of the whole product lifecycle management of a product or system at Elm, from design to production to use it in the field process? This one I asked.
Okay, yeah, in our case, we don't have the whole product management, the whole product life management, because it's an old factory, so a lot of things are on paper or in old softwares, so we don't have a lot of things. But we do have the data, like when a boiler is made, it's scanned on every workstation. When they make their technical work on a boiler, they have little code bars, and they scan, so we know how much where the boiler is on the workstation, and we also know the result of the test. For example, the hydraulic test and electrical test. We know the result of this boiler. So this is the product health management. This the only information that we have. We also know where it will be sent, but we don't have the whole thing, the whole digital twin of the boiler. We just have a few information on this.
Yes.
It's still a new approach of industry, so it's hard to make change because we gave them an AR training app, and they're still not using it, even if they have a lot of errors on the new production line. So there is a high inertia to change, and so it's hard to make them use the digital twin and the new technologies.
Okay, let's ask one more maybe. There's a last question, not to exhaust you. So I actually highlighted an article for maybe also the audience. I don't know who put that. You can take a look at it, this article. The question I wanted to ask among the remaining ones is, how do users respond? Do they like it?
So we had two types of users in my tests. We had the production line chief. So they were like, okay, it's easy to use, okay, but they didn't know why they were doing this. So we explained to them, but it was hard for them to see the big picture. And we had the methods engineer, so the ones who designed the production line. And so they were like, oh yeah, that's good. Oh, we could use it for that. You could use it. Oh, it's wow. So they were a lot more excited. But yeah, usually the operators, they didn't know what the digital twin was and why did we work on that. But the training tool, they were a lot more excited for this one, because they could see what was the use. And so we had to say them, yeah, but this is the first part of the training tool, so you have to represent the workstation in order to attach the instructions. So when you move the workstation, when you change the boiler model, you just have to change the thing, and then yeah, you can have your instructions. They're like, okay. So they were okay. They were excited to use new technology, but it's more on the management on top, like the production chief. He never tried, and they didn't want to change things, so it's hard to make them accept change.
Okay, I would say that's all for the questions. We thank you. Thanks for answering also quite a lot of questions.
Perfect.
No
Yeah. So
problem.
then
Thank
also
you,
big
everyone.
applause for you, Pierre. I enjoyed it a lot, and also you get the speaker present with lots of nice ingredients. Very good.
Thank you.
So.